Alright, hi guys. In this video I'm gonna go through the 2024 mechanics paper for level 3 physics. So let's start. Question 1, circular and rotational motion. Okay. So for the first question, question 1A, in one trial the ball bearing reaches the bottom of the first dip with a velocity of 0.85 meters per second. Calculate the angular velocity of the ball bearing when it is at the bottom of the first dip. So we want to look for the ball's velocity here. But before I start, I'm just going to do some unit conversions here. So we have that the radius is going to be 7 millimeters or 7 over 1,000 meters. And then we have that the mass, m, is going to be 11.2 over 1,000 kg. and and the radius. So I'm just gonna call this instead the height, because height. So okay, so the relative height at, I don't know, any position. Just call it, actually, we'll just say the height at y is just going to be 35 over 1,000 meters. So we have to calculate the velocity, the angular velocity of the ball. Okay, so I think for this one we can just use the equation, the relationship V equals R omega, which implies that omega is just the ratio between the velocity and the radius. The velocity is 0.85, so 0.85 over the radius is 7 over 1,000, which is, I'm just going to put that in my calculator. 121.43 radians per second, which is 121 rads second to three significant figures. Let's move on to the next one. Show that the maximum speed is 0.586 meters per second in order for the ball bearing to remain in contact with the track while going over the bump at point Y. So what this basically means is that, okay, over point Y. So let me delete this. So basically, in other words, when the ball is at the point Y, we can't have an excess force going the vertical direction. So the only possible value it could be is zero. So then the vertical force here is equal to zero. In other words, the force pulling it down and the reaction force from its weight force should be equal. So I think we start this one by saying I don't have to draw anything, right? No. Okay, so FC equals FG, right? Because we want the two forces to be equal. In other words, if we take this other side, FC minus FG equals 0, and vice versa. So then we can just substitute the equations. So mv squared over the radius is mg, and then we can just rearrange this to get v equals the square root of the radius times gravity. And then continuing the calculation here, v equals the square root of what's the radius? The radius was, I think, 7 over 1,000. So that's just going to become 7 over 1,000 times 9.81. And if I put this all in my calculator, um, oh, wait. I didn't even realize. Okay. Oh, okay, I should be putting 35, not 7. I read the wrong one. Um, Wait, did I write that correctly up there? R Okay, I'm gonna replace that with RB. That way it's less confusing. Okay, and then when I put that in my calculator, I get, um, okay, there we go. Now I get 0.58596, blah, 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 meters per second. And then to three significant figures, that would become 0.586 ms minus 1. There we go. Okay, cool. Let's move on to the next one. Compare the forces acting at the top, point Y, and the bottom, so point X of each bump, and hence explain how the net force varies in these positions. Okay, so let's draw our first one for point X. So we know that we would have, at this point, we obviously have a weight force, right? mg. But we've also, because if you kind of imagine it like as a circular loop, then you would have an unbalanced, you'd have a centripetal force acting to the center, right? And so in this case, what we would also have a reaction force, which would be that would must be greater because we've got a net force going towards the center, right? In circular motion, there's an unbalanced force acting to the center. So there would also, that means that there would have to be some Fr, not to scale obviously, but just to write that Fr is going to be greater than your weight force, and we also have the result that your centripetal force should be equal to the difference between your reaction force minus the weight force. So that's the centripetal force acting to the center. And I think that completes that one. We'll obviously get to like the like comparison bit in a bit, but like first let's try to get like our mind on what's going around. And then for this one we can sort of similarly just imagine it like how could we imagine it? Sure, good enough, and then just sort of just yeah, just imagine instead it's at the top of this imaginary loop because the equations would still hold. Um, and basically at this point we would have our like let's start with the obvious force. So mg pointing down, and then we also would have, because it's got an unbalanced force acting to the center, so it would have a centripetal force Fc acting to the center, but we would also have a reaction force, right, in the opposite direction. So let me write oh, at point X. And then at point Y, so for point Y, we would have the result that actually the force acting to the center must be larger than the force that's acting away from it. So mg must be greater than Fr. And we also have the result that in this case, your net force acting to the center, or Fc, would just be the difference in your weight force going down and your reaction force. So mg minus Fr, and that will give you your net force going down because I mean it's you gotta have a non-zero, a positive force going to the center, and so this is at point Y. Okay, cool. So now I think we can start getting to the explanation. So let's I'm just gonna summarize this. I wouldn't say like write this in an exam for full marks, but you can elaborate on what I write. So at point X, let's just start with a typical answer. I don't know. At point X, your reaction force, what's happening? It's pointed to the center of this imaginary loop. At point X, your reaction force is pointed towards the center of the circle. Here we go. And I should get rid of it. It's pointed towards the center of the circle and um is larger than the weight force, which results in a net force uh acting, actually I should write pointing upwards So that's just kind of a rough explanation for what's going on at point X. And then we can similarly write something for point Y. So and then so similarly at point Y, um, the reaction force is still pointing up, but your weight force, which is mg, um, is still less than mg because our gravity force is providing us centripetal force less than mg because how can I say it? Yeah, because m less than mg because mg provides fc and fc points down. Cool. So that's just like a really rough explanation, like sort of like what you should like in the base case have, but I suggest you elaborate on that more if you can. Let's move on to the next one. Question D. Okay, so by considering energy changes, calculate the maximum height h above the top of the first bump point y that the ball bearing can be initially released from if it is to remain in contact with the track as it travels over the bumps. Ooh, okay. Okay, a cool conservation of energy question, like a kind of like a scholarship question, but I don't know how hard this one will get, so we'll find out. So basically for this one, so in other words, what we're trying to find is that the energy the ball has up here, right? We'll just call it EI, should be equivalent to the energy the ball has got at point Y, so EF, and that should be equal to EI, right? So let's go ahead and write that out first, right? So we have the result that your initial energy should be equal to your final energy, right? And so now the energy that the ball has at the top is just purely gravitational potential energy. It's not moving, it's not rotating, so it doesn't have any kind of energy, right? Other than gravitational potential energy. So that just directly implies that your potential energy is to be converted into some other kinds of energy that the ball has at point Y. Now, sure, right? The ball's moving in that direction there, but it's also rotating, right? And so that means that we have to consider the fact that it would turn into kinetic energy plus EK rotational energy, right? It doesn't have it doesn't have gravitational potential energy because I'm assuming that this is the line h equals 0. And so because we're calculating the height of the ball above y, so the relative to y, this should be 0. And so I think that's about all, and we can start constructing our equation now. So the energy that the ball has at the top is just mgh, and that is to be converted into half mvy. I'm writing vy to denote that it's the velocity of the ball at point y, plus half I omega y squared, right? And so what we can go ahead and start doing is substituting some numbers in rather than just solving this. So let's go ahead and do that. So we get half mvy squared. We don't have to substitute anything for that, I think. And then plus half. Oh, okay. So they've kindly given us the inertia here, which is 2/5 mr squared. So let's go ahead and put that in. M times the radius of the ball squared times the angular velocity of the ball at point y squared. Now keep in mind the relationship that Vy is the radius of the ball times the omega uh, at the point y. So omega y squared is just going to be all of this squared and this squared. And so that just directly implies that omega y squared is just the ratio between your velocity at y squared divided by the radius of the ball squared. And we can go ahead and directly substitute in this result. So vy squared over radius rb squared. And then let's start simplifying. So half mvy squared plus this will become 2 over 10, which is 1 over 5. And then m, and then this rb and this one will cancel out the radius of the ball, so mvy squared. We can go ahead and now add these two. Actually, before we add the two fractions, I'm just going to cancel this unnecessary mass term here. So we just get the result gh equals half vy squared plus 1/5 vy squared. And so gh is just going to be 5 plus 2 is 7 over 10 vy squared. Now, I think we could just maybe simplify this a little more, because if we go up, I think we had an equation. Vy, the velocity at point y is just the square root of the radius times gravity. And so we can just go ahead and substitute in that result. And so this would just result in the fact that GH is equal to 7 over 10. Let's see, root HYG. And so V squared is just going to be HYG Hy times gravity, and so we can just go ahead and cancel the g's, and we obtain a pretty nice result that actually the height of the ball should just be 7/10 of whatever the height of the thing is at point y. And so we can just go ahead and punch in our numbers now, because then in this case h would be 7 over 10 times, what's the height at y? 35 over 1,000. 35 over 1,000. 35 over 1,000. And that gives me 7 over 10 times 35. Oh, that's a really... Oh, actually, wait. 0.0245 meters. Or if we convert that back to the initial units that they gave us in millimeters, that would be 0.0245 over 1,000 or I don't know, whatever that is, 0.025245 over 1,000. Yeah, okay, I'm not gonna bother writing that, so we can just leave that like that. So that's my answer for question D. Now let's move on to the next one. Question 2, rotational motion. A golf ball of this mass here is placed into a cup. Okay, downwards at a constant rate of 1.83. Show that the angular acceleration of the flywheel is 16.6 radians per second. Okay, so I think we can just use one of those, what is it, A equals R alpha or something? Here, there we go. Your linear acceleration is just your radius times your angular acceleration. So we just have the A equals R alpha, and alpha equals a linear over radius, which is our linear down constant at 1.83 over the radius over... okay. So we can then just multiply this result by 2 and half this by multiplying the numerator by 2, I'm essentially just halving the bottom. So this will just become 0.22, which is going to give me a result. It should give me that number there, 1.83 times 2 divided by 0.22, and I get 16.3, 16.636, blah, 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 radians. Second minus 2, which to three significant figures is 16.6 radians per second. And so if the ball and cup start from rest and fall through a distance of 0.75 meters, calculate the final angular velocity of the wheel. Okay, so we can, I think for this one, the first equation that came to my mind is the fact that VF squared equals VI squared plus 2AD, and VI is 0. So we can just get the result. VF equals square root 2AD, which is just the square root of 2 times 1.83. 2 times 1.83 times 0.75, which gives me a result of 1.66 meters per second. Okay. And so then what we can do is we can just actually I'm gonna try to obtain actually a more precise answer. So if we go back this way, we know that VF equals R omega F, so then I can just equate this and this such that we get um I'm asked to find the final angular velocity. Yeah, so I can just do that. So then we get R squared omega actually hang on. We get that R omega F is equal to square root 2AD. And so from here, this just is going to be what? Final angular velocity. So then that would just be omega F equals root 2AD over R. And so I'm just going to use my same result from here, 1.66, and divide that by the radius. What's the radius? 0.11. And that gets me a final answer of like 15.09 radians per second, which is about 15.1 reds. Second minus 1 to 3 significant figures. Right, so for this next question, we have to calculate the rotational inertia of the flywheel. Begin your answer by calculating the force that is causing the flywheel to accelerate. A free body force diagram may assist you in calculating the tension in the string. Okay, it's an interesting question. Okay, so I'm just gonna draw my thing out first. So we've got like some of this object, the flywheel, and then we've got the object. Let's see. Let's start drawing the forces. So on the center of mass of this object would have a weight force, F weight, and that's just going to be uh, F weight is just going to be mg, right? And similarly, we're also going to be having some tension force acting upwards. We'll just call that F tension. But if you remember, they said that it will accelerate downwards at this constant rate. So what that means is that your net force, F net, is just going to be downwards, and it's going to be mass times whatever it's accelerating at. And so your tension force that's going up is just going to be the difference between the weight force and your net force. So we can write that as Ft is just going to be this minus this, because there's a small gap, and so that gets inverted back. So mg minus ma, and so that's going to be the tension force that's acting upwards in the string. Okay, so now that we got that, I think that's so we've calculated the tension in the string. Okay, cool. Now, what could we do next? So, since we've got the tension force, let's see. What should we calculate for? Okay, cool. So we have the result. Your torque is your perpendicular force times your radius. Now, in this case, the actual equation for torque is like tau equals FR sine theta. But because it's at 90 degrees, this term goes to 1, so that's why we write torque is force times distance. Anyways, that's just for your own understanding, but let's move on. So a more like situation specific equation for torque would be for the tension force times the radius of the object. And we also know the result that torque in rotational mechanics is also equal to the inertia of the flywheel multiplied by its angular acceleration. Cool. So we have a nice equality here. So we can go ahead and write I, move down a little bit. We can write that I alpha is equal to your tension force times your radius. And so our tension force, we calculated I alpha equals R bracket, I think it was mg minus ma. I'll double check, but I hope that was right. mg minus ma. And we also know the result that A equals R alpha, which implies that alpha is just your linear A over R. And so I times A over the radius is equal to R bracket mg minus ma. Oops. And then we can just go ahead and factor out an m also. So we get IA is equal to r squared m bracket g minus a. And so your inertia is going to just be mr squared over your linear acceleration times the difference between your gravity and acceleration. And then we can also factor out the acceleration to get the result that I is equal to mr squared bracket g on a minus 1. And I think that's about as complete as it gets. Now that all we got to do is just punch in the numbers. So let's go ahead and do that. And so I is just going to be mass. So what's the mass? 0.046. 0.046, and then your radius is the diameter, actually, the diameter over 2, so 0.11, 0.11, and then your gravity is 9.8. I forgot the linear acceleration. 1.83? Yeah. Okay. 1.83 minus 1, and let me put that in my calculator. And then 0.046 times 0.11. Wait, let me check the units before I finalize everything. That's meters per second. And yeah, okay, cool. They haven't put any tricks in here. That's good. And then we'll take the ratio 9.81 divided by 1.83 minus 1. And okay, there we go. And I get a final answer of 2.427 times 10 to the minus 3 kg meters squared. Yep, kg meters squared, which is 2.43 times 10 to the minus 3 kg meters squared to three significant figures. Or alternatively, that is 0.00243 kg meters squared. Nice. I hope that's right. Okay, let's go. Let's move on to the next one. Explain what will happen to the final velocity of the ball and cup if the flywheel is replaced with a solid disc of the same radius and mass as that of the flywheel. Okay, so now we have a solid disk here. Let's just go back. If we take a look at this one here, we notice that most of the mass is just concentrated in this region here, and this is your central axis. So all your mass is like really far away, right? So that means it's got a higher inertia because I think inertia is like kmr squared, where k is some constant. Um, but we don't have to worry about that. But like basically the idea is that inertia is proportional to the distance that the mass is away from the rotating axis. So in this case, it's further on average. So it's got a higher inertia, right? And in this case, what's happened is now we've just kind of got mass all over the place. So technically, if you think about it, on average, the mass would be closer to this axis of rotation than it is for the other one. So what this means is, if I had to put this into words, right? Um, using a solid disk, basically, I'm just gonna like simplify this. You can expand this and put it in your own words. So I'm just gonna give you like a rough idea of what you should probably write. So if you use a solid disk, then that means that your mass distribution will increase, right? And since your mass distribution about the rotating point increases, um, that means that your total. Oh, okay, I should actually write that. As inertia is proportional to the distance squared, right? Your mass distribution increases, and so what happens? Oh, sorry, that's wrong. It decreases, not increases, it decreases. So actually what happens is that your inertia will go down as your distance on average is gone down. So what this means is that your on average inertia, because it's in a rotating case, we could probably write rotational inertia, but we'll just keep it to inertia for now. Which means your average inertia will decrease. And so we can use, I think, a similar result from before, right? So we know that your inertia is, like, if we just expand this out, mr squared g over a minus mr squared. So we clearly see in here, right, that inertia is proportional to the ratio between the gravity and the acceleration, right? So basically, a smaller inertia means a larger acceleration, right? So if your inertia decreases, then your acceleration must increase because gravity is constant. And another way to look at this is we know that V equals R omega and A equals R alpha. So if we solve for R, then we get V over omega is equal to A over alpha, right? And so a larger acceleration implies that you will have a larger velocity. And so you can put that into words, but I think as a rough idea on how you should approach it with what kind of theoretical concept you should go, this is kind of, I think, the way to tackle it. So I don't think I'm missing anything for that. I've the final velocity will increase pretty much. I guess maybe you could also use the result that the final velocity squared is just going to be 2 times your acceleration times the distance it falls through. So a larger acceleration means you'll definitely have a larger velocity. Let's move on. Question 3. Simple harmonic motion. A ball bearing is released in a watch glass and rolls back and forth with simple harmonic motion of radius of curvature r. Okay. State the two conditions necessary for it to be moving with simple harmonic motion. So first one is that you're restoring force x to equilibrium. And the other condition is that your acceleration should be proportional to your displacement. I hope you can read that. Okay, that's not an S, that's meant to be a C. Displacement. And for this next question, the ball bearing is released 0.04 meters from the right of the equilibrium position, and it oscillates with a time period of 0.882. Okay, so that, and using a reference circles or otherwise, calculate the displacement of the ball bearing after 1.2 seconds. Okay, so what that would mean that, well, it's released 0.4 meters from the right of the equilibrium position, so 0.04. Okay, so I think first of all, let's figure out what equation we're going to use. Because it's released from maximum amplitude, we would use A cos omega t. And the reason for that is because of the fact that cosine of 0 is 1, which indicates it's being released from maximum amplitude. So we can go ahead and just write our equation y equals A cos of omega t. And we know that the fact that the maximum displacement is going to be 0.04, which is at 0 seconds, which is why y equals A, and hence why we use the cosine expression. So 0.04 cosine of, let's work out omega. We know omega is just 2 pi over time period, which is 2 pi over 0.882, 2 pi 0.882 times t. T is just 1.2 seconds. And then that's going to be 0.04 cosine of 2 pi over 0.882 times 1.2. And my calculator is in radians, so I get a displacement of negative 0.0256 meters. Cool, nice. I think that's about it. I've calculated displacement. Now let's do C. Eventually the ball bearing comes to rest. Using the axes provided, provide a labeled graph of the displacement versus time. So this is going to be time. Let's start at positive max displacement, negative A. Okay. Okay, cool. Okay, so these kind of like ones, they follow like a shape, like something like, no, I'm just gonna draw like more of exponential decay. So it's going to start from maximum amplitude, and then it's going to like go down, and then, oh my God, this is gonna be horrible. That's first T, and then that's your second T. That's going to be a third T, fourth T, and oh my God, that is okay. Okay, that should be all right. I think that's enough to give you the idea. That's going to be T, 2T, 3T, 4T, 5T. So I think the key idea is as long as you have an exponential decay and you have this T, 2T, 3T, 4T, 5T all out, you should be all right, I think. It's really bad, but I mean, it might be easy on pen and paper, but I kind of suck at drawing, so yeah. Anyways, let's move on to the next one. Name this phenomenon and explain in detail why the ball bearing eventually comes to rest. Support your answer with any relevant formulae. Okay, interesting. Okay, so I'm just going to start with the most obvious result. This phenomenon is called damping. You might have covered in class. Uh, Damping, yep. This phenomenon is like damping. So basically, let's just start by like in theory, in theory, energy for this kind of system, right, would just transfer, energy transfers between EK and EP, right? Or in other words, kinetic energy and gravitational potential energy, because I think it's along some surface like this. So when it's over here and over here, then it's called energy, gravitational potential energy. Sure, we could consider rotational kinetic energy, I think, but I don't think it really matters, right? I dot E. Your total energy of the system is just going to be a composition of kinetic plus potential, right? That's my first formula stated, I think. And then, in reality, however, in reality, uh, energy would be lost to the surroundings. Energy lost to the surroundings, and this could be due to what could heat, for example, heat produced from friction, heat produced from friction, and so ET. And so your total energy will decrease, right? So then your mgh would also relevantly decrease, and which just implies that amplitude also decreases. You could obviously write a more better answer than me, but like just as a rough guideline, I think this is about it for that question. And we're done, thankfully. All right, I hope that helped.